Hi there. Now let's continue with another LeetCode. Today we are looking at problem. Sorry, give me 1 second here. Alright, so this is problem 124. Binary tree maximum part sum. A path in a binary tree is a sequence of nodes where each pair of adjacent nodes in the sequence has an edge connecting them. A node can only appear in the sequence at most once. Note that the path does not need to pass through the root. The path sum is a path. The path sum of a path is the sum of the node's value in the path. Given the root of a binary tree, return the maximum path sum of any non-empty path. Okay, so a path. Let me reread the problem to make sure I understand the problem. A path in a binary tree is a sequence of nodes where each pair of adjacent nodes in the sequence has an edge connecting them. A node can only appear in the sequence at most once, so that the path does not need to pass through the root. The path sum of a path is the sum of the nodes' values in the path. Given the root of a binary tree, return the maximum path of any non-empty path. Alright, so we are given binary tree and we need to find the path. So basically a series of we are given the tree root. There we would like to find the max of a series of nodes. Okay, or I would say series of connected nodes. Alright, so let's look at the examples there. Examples 1. We have 1, 2, 3. The maximum here is if we pass through all of them, which is 2, 1, 3. So that would be 6. Example 2, we have -10, and then 9, 20, 15, and 7. So let's say the maximum here. On the left part, if I take that, then that would be -10, -1. So I better not take the -10 and 9. So how about I just take all of the right subtree. So 15, 20, and 7. That would give us 30, 42. 42, yes, 42 is the answer. Now I would like to clarify a few questions. And I'm thinking about what else could be relevant to know. So, clarify. Can I assume that the nodes, can I know the number of nodes? So you're given the number of nodes is between 1 to 3 times 10 to the power of 4. Okay, and node value can be negative, yes, like we have seen that in the example 2. Alright, I think I understand the problem now. may think of. Now I will proceed. Now I will try to think of some possible approaches to solve this problem. So from the examples above, I observe a few things. Okay, let me just break it down into the smaller problem. So if we just have a node, then we would have to take it. Okay, so if that is just one node. One node, then the node itself. If there are two nodes, say if there are two nodes, then the output would be max of the max of two nodes. So A plus B, A and B. So here I'm gonna write down findings. Okay, and then node itself. How about there are three nodes? If there are three nodes, then what I'm gonna do is I need to check. So three nodes, I think I need to break it down further. We have A, B, C, or A, B, C. So in the first example, where A has two children, which are B and C. So this one would be max of A on the max of A plus B or A plus C or A plus B plus C. So there are four possibilities. Either I pick only A, or I pick A plus B, or I can take A plus C, or I can also take A plus B plus C. How about the three is A, B, C like that? So this would be max of A. I think this could be breakdown into two problem, into a subproblem. So it's either max A or max of A and max of A plus B, A plus solution of the sub 3V. No, actually. Let's see. Okay, so I just had a thought here. So if we have a node, a root node, the solution would be either, okay, so let me write it down here. So solution of root, this would be the max of solution B plus A plus solution of C. Okay, or it could be just solution B, or it could be solution of C. Okay, so either we take the take A, let's see here. So either the part, there is a part that ends at B, and then we include A, and then we include the C if there is any. Or we could just find out what is the whether there is a part in B that provides us a better solution. Or we could also find a better solution in the subtree on the right chart. Okay, so I think this could, I need to, so how are we gonna know that solution B would include B itself, right? Because, okay, I think I got an idea here. So a part would be either actually, yeah, so I think if we break down the problem into its sub-problem, then at the end we would have a node with two chart, or even just one chart, or even no chart. So if there is no chart, then we have to let that node, or we could drop that node, so we are not using that at all. So that would be in my findings 3, where we have 3 nodes, A, B, C. Then the solution would be A, or A plus B, or A plus C, or A plus B plus C. Or we could also find the solution at B and solution at C. Actually, so if we further extend it into, say, 4 nodes, then I think this is a recursive problem. Yeah, so solution of the root is the max of solution of B plus solution of A plus solution of C, or it could be actually, or it could be solution B hmm, Okay, so I just had a thought here. So I'm thinking that if we, so the maximum, so I mean the solution given a node could be, okay, let me rewrite the nice answer that solution of a node, this could be max of yeah, so solution of left plus a plus solution, actually it's not the solution, but the how about I call it max, and okay, so let me write down n here. So n here I'm gonna define it by a part that ends at a node. So n of left plus a plus n, or I think better name would be stop. Let me think of better naming here. Let's call it the can't think of better name. Okay, let's call it connect. Connect means that I can attach A into the part of the left side. So I'm gonna define it later. So just stay tuned on this. Connect. Oh, right. Or it could be connect actually. So solution, let me define the solution of mod. Or I could say, I think I better call it max of node. So max of node means that a part that contains a node. So this would be solution that has the node. Then here I'm gonna define connect. The connect of a node is the max of 0, meaning that I don't take itself, or it could be just itself, node, or it could be node plus connect of left, or it could be the node plus connect of right. Okay, so I don't take any of it. I don't take that side, or I take itself only. Or I could also take itself, and then the left side, and then the connect of left and connect of right. Wait, I can't take both connect left and connect right because that would means the node is not ending at the node itself. So let me define the connect means that a part so connect means that, let's see, solution that ends at the node. So okay, I think it's a bit ambiguous on the first one, so I'm gonna call it solution instead. Solution that has the node. Okay. In the end, fine. So the final solution is we find all the nodes. We check all the nodes and then we get the solution of the node. So now we just need to find the max. The maximum of every node, every solution node. Alright, I think it makes sense here what I'm doing. It kind of makes sense to me. So what we are doing is essentially finding for each node, we recursively find the solution. So let me try it out with the examples that we are given. So first one, we have 1, 2, 3. Connect equals C, solution equal S. So I'm gonna put it inside a bracket, which represent the connect and the solution. Okay, so we have 1, 2. Let me give it some space. 3. Okay, here at node 2, the connect is 2, solution is 2. At 3, 3 and 3. At the node 1, connect is 3, 5, 6. And the solution the connect and the particular node is, let's see, we either take the node and connect it left or connect it right. So in here it will be 4. And then solution is we add up all the connect, which is 6. So 6 is the solution, we got it right. Second examples, we have minus 10, 9, 20, 15, and 7. Okay, so 15, we have 15 and 15. 7, it is just 7, 7. So at the root node, the solution is just itself, because there is only one node. And then here at 20, what is the connect there? Connect is either we take the, I think it's pretty obvious, it is 35. And then connect is we add up all of them, which is 20, 35, 42. And then in here, at the root node, we have minus 10. So minus 10, we are not going to take itself. How I connect to left, it's still negative. We connect to the right, which gives us, how much is that? 35 minus 10, which is 25. And then the max would be, we add up all of them, which gives us 42 minus 10, 32 plus 1, it is 41. And you see that solution, we take the max, which is 42. Alright, I think this kind of makes sense to me. Does it sound reasonable to you? I'm pretty good about this and would like to start coding unless you would like me to explore further optimizations. Alright, so let me code this up. So we are given the max pad sum of the root. So there are two things that I'm gonna compute here. First one is the connect and also the solution. And here I'm thinking that I'm gonna create another function to help me do all of this recursively. So let me write down, let's start from the function given by the question. So we have max pad sum. Maybe I don't need to do that. Okay, let's just call it max solution. So call it MA equals the root.val. I just initialize it to any value. Actually, I just noticed one thing. So the solution has to be non-empty. So the solution that includes the node is the max of node and we are using the connect. So let me amend what I wrote before. Solution of a node is the max of the connect left plus node plus connect right and the node itself. Hold on. Okay, I don't need to do that. Sorry about that. Because the connect is 0, then it just itself. Right. So the main is root 12. Now we define a function called connect, and it will receive a node. Let's just call it a node. Here, what we're gonna do is we need to check the left and right. So connect at, okay, so if node is a null, then it's 0. Okay, because there is nothing to connect to. Otherwise, if we check the left, connect node dot left, and then the right, connect node dot right. Then the solution would be return. Okay, before we do that, don't forget to update the max solution. So max equals max of max, and let's see, left plus node dot l plus right. Okay. So now we return the solution. It would be the maximum of 0 or not dot 12, not dot 12. Can I use the max there? Yeah, I think so. So max of left and right. In the end, I'm gonna call the connect at the root node, and then we return the max. Right? Now let me go through the code again to make sure I don't miss anything. First of all, I initialize the maximum solution as the current root, and then I'm gonna create a function called connect. Now connect will return a part that ends at the root node. So if it is the null pointer, then there is no part that ends at there. So I return 0. Otherwise, I could check the left, connect, and the right connect. At this point, I could tell that the maximum solution, if it includes the current node, it would be the maximum of the current maximum we have seen so far, or it would be, or it could be the current, or it could be a path that includes the current node. So that is what I'm checking in the max there. And then in the end, we return. We need to, because we are trying to look for a path that ends at the root node. So if there is no good path there, meaning that it would be returned negative, then in the future we might not want to consider even a path that ends at the current root because it would be negative. So that's why I put in the 0 there, and then check the current value, or there could be a path that includes one of the left connect or right connect. So we could get the max there, and then in the end we return the max. So let me quickly go through the example there to make sure I don't miss anything. Connect the node. We check the left, and then at the left we have 2. The left and right will return 0. So the max would be just itself, which is 2. Now we update the solution to 2. And the max of the connect of 2 would be just 2 itself. And then same for 3. And then back to 1. We have the max is the max, we update it to 6. And then the connect would be, connect we don't care at that point. So that's how we got 6, which is the correct answer. Now the second example, we have, so all the root node will be initialized to itself. And then at 20, the maximum would be updated to left plus value itself plus the right, which is 42. And then the connect would be, in this case, we take the left part in itself. So that would be 35. Back to the root node, which is minus 10. So we don't care about the connect at that point, but the max would be left, which is 9. 35, which is 44, but then we subtract it by 10. So it gives us 34, which is not the solution. So again, it stays at 42. Alright, let me quickly put it into the LeetCode. So make sure we got this right. So we define connect at, I just use the root here. Or is it not a good one? Okay, let's just call it node. To me, it sounds more generic. If not node, return 0. Otherwise, the left would be the connect at the left. Then we do the same for the right. So yeah, remember to update it. Yep, and then the solution of connect would be the max of 0, not the found. Or I think in this point we could do a max of 0. Can I do it all at once? Let's see. Left, left, and right. Connect of return max. Okay, let's try to run this. Max equals left. Okay, so max is not accessible. Okay, how about this? We are going to store this into a solution. So let's call it cut. Then we return max. No, I think a better way to just put it into external non-local mark. Yeah, so we got it right. Let's try to submit it. Hopefully we got this correct in one go. And yes, we got it right. Memory is very efficient. Solution is not the most efficient. Now let's look at some example. Next pad, left and right. Next some. Yeah, this is exactly what I'm doing, right? Okay. Let's look at the next solution. Yeah, this is also what I am doing. Okay, I think the algorithm is more or less like that. So I'm gonna stop here and see quickly. Alright, thank you everyone. I think we will stop here.